Hello, hello, class. Welcome to AP Chemistry. This is a series of video lessons that will support your journey in AP Chemistry, and we're starting with some chemistry fundamentals. This particular packet uh, was originally created by Renee McCormick through the National Math and Science Initiative, and then I've heavily modified and added in some extra practice as we go. So you're seeing a modified version of that document here. As we go through, I recommend taking notes. I recommend completing all the practice examples we do together, and then even doing the additional practice that are there for you in order to support your learning. Let's get into it. So first, chemistry and overview. We are studying chemistry because chemistry is the study of matter, which we know takes up space, has mass, and exhibits inertia. Matter is composed of atoms, currently of which there are 118 unique types of atoms or elements on the periodic table. Uh, all the more recently discovered ones have been created in a laboratory setting through a lot of different experiments. Um, but we'll primarily spend our time in AP Chemistry focusing on elements that have been found in nature and how they react and the different kind of patterns that they undergo. Water, for example, is made up of one oxygen and two hydrogen atoms. It has a formula of H2O. And if you pass an electric current through water, you can separate it into its constituent atoms, which would be one molecule of oxygen and two molecules of hydrogen for every two molecules of water that you split up. If you've taken a chemistry course before, yes, that is a balanced equation that I just talked about. 2 moles of water gives 2 moles of hydrogen and 1 mole of oxygen. What's really unique about this, I like this diagram a lot. This is called a particle diagram. We're going to see these quite a lot. It is a visual representation of your molecules. So we have a red oxygen atom and 2 hydrogens. And then over here you have 2 oxygens and then 2 hydrogens. Chemical reactions can also be reversible. So the one I just mentioned is splitting water up into its constituent atoms. But if you ignite those atoms through a combustion reaction, you can also get water back. As we stated before, chemistry is the study of matter and energy, and more importantly, the changes between them. The scientific method is going to be an important part of this course. Uh, One thing I should say about this particular packet is that many of the items in this packet are not linked specifically to objectives in the current AP Chemistry curriculum, but they're considered prerequisite skills, meaning things you should know before going into AP Chemistry. If you don't know these things yet, that is okay. That's why we're going through them now. So first up is the scientific method. You will have to do labs in AP Chemistry, and that requires you to make observations, formulate hypotheses, and perform your experiments. You'll even get to the point where you will need to design your experiments and come up with your procedures to do so. We have both qualitative and quantitative observations, ones dealing with uh, the properties or the characteristics that you can observe, other are dealing with actual measurements that you can make. We're going to spend a great bit of time talking about measurements in this course. It's also a good time to talk about theory versus scientific laws. Theories are hypotheses assembled in an attempt at explaining why the what happened in an experiment, whereas a scientific law is a summary of observed measurable behaviors. Theory is an explanation of the behavior, the law summarizes what happens. So that is very important to know the difference of. We're also going to use models to help explain natural phenomena throughout the course. One of those models, as I mentioned before, is a particle diagram. There's going to be a lot of different modeling that we do in this course. A couple of laws to review. The law of conservation of mass. That means the mass of the reactants is equal to the mass of the products after a reaction is performed. Essentially, no mass can be created or destroyed. Same goes for energy through the first law of thermodynamics. It's very hard to control all of our variables, as we will see when we get to thermodynamics, but energy cannot be created or destroyed. It can only change forms. All right, let's get into some measurement. So, units of measure. Measurement's probably going to be one of the more important aspects of chemistry, and we need to measure things appropriately. So, again, anytime you have a number that you are reporting, there's two parts to any measurement, the number and the unit. You leave off units, you will be subject to losing some points, and we don't want to do that. In the United States, we have the English system, which honestly does not do us much good here in chemistry class. We're going to stick with metric, or the SI system, which is Système International, which is French. This is an internationally agreed upon system that primarily is derived from the metric system. All scientists use SI units. I would take a minute and pause and read through all of these physical quantities, the names of the units that go with them, and the abbreviations. You will be responsible for memorizing these units and abbreviations, with the exception of candela. We don't need to know really anything about luminous intensity. So you can cross that one out, but the other ones you should memorize. You should know a couple of your conversions here. The big one is 2.54 centimeters equals 1 inch. I use that one quite a lot. And then for scientific notation, these ones that are in blue, you should know what the prefix is, and then you should know what the exponential notation is and what that means, and how to convert between scientific and uh, normal standard notation. The big ones we're going to use a ton in chemistry are milli, centi, and kilo. You could also run into micro or nano fairly often, depending on the problem. So again, memorize these. A couple of ones I added in here. 1 cubic centimeter is equal to 1 milliliter, which, if we're looking at the density of water, which is 1 gram per ml at certain temperatures, then that is also equal to 1 gram of water. If you hear the term cubic centimeter or centimeters cubed, that also might be abbreviated as cc's if you're someone that wants to go into the medical field. If you ever watched any shows, medical related shows, and they say, oh, deliver this many cc's of whatever medicine, that's what they're referring to, cubic centimeters or millimeters, or milliliters, sorry, in this particular scenario. The other one you need to know, 1,000 milliliters is equal to a liter, and that's equal to a decimeter cubed. Volume. Volume is going to be a really interesting one, because this is where a lot of measurement comes in chemistry. We measure volume all the time, specifically volume of liquids, in which we're going to need to use milliliters and liters as our units. Now, you do need to know your glassware, and you need to know it well. There are several different kinds of glassware in chemistry that we're going to use. Some of them are used for measurement. Other ones are just used for holding liquid. So the 4 that I've listed here, graduated cylinder, pipette, burette, and volumetric flask, these are ones that are good for measurement. And you need to know how and when to use them. Graduated cylinder is probably the one you're going to use the most often for measurement. Um, if you're making a solution of a particular concentration, you want to use a volumetric flask, because it has only one specific calibration mark. You can only ever measure a volume of 250 mLs with a volumetric flask of this size. There are smaller volumetric flasks, but again, they can only measure one specific volume. Same goes with a pipette. Volumetric pipettes also measure one specific volume. A burette is also a really good one that has a lot of different markings, and that is used for dispensing a really specific volume of liquid. So you'll probably use the burette and graduated cylinder most when it comes to measuring, and you might use a volumetric flask occasionally when it comes to making a solution. Big no-no, do not ever use an Erlenmeyer flask or a beaker to measure things. They are meant to hold samples and reagents and to conduct reactions in, but they are not ever going to be used for measurement. Please know the difference. Okay. For mass and weight, now there is a difference between mass and weight if you get into the physics component of things. Primarily, we can say that the acceleration due to gravity is constant on Earth, so mass and weight will be the same uh, for all intents and purposes in this course, but you need to know that they are not the same in real life. If you were to go to the moon, the mass of something stays constant, but the weight is what changes due to gravity. We weigh things on a balance, not a scale. If you access the link here, you do need to know your labware for AP Chem. This is a great website. Here's our balance, ring stands, scupulas. Yes, scupula is a thing. I believe in honors chemistry and regular chemistry, people always laugh when I say scupula. I'm like, it's a real thing. What? Um, but we've got our tongs, strikers, all this good stuff. You should know what each of these things are, what they're used for, what they look like, because we're going to use just about everything on this list. All right, precision versus accuracy. Since we're on the topic of measurement, we need to know how to measure accurately, also precisely. Accuracy refers to the correctness. It is agreement of a measurement with the true value. Uh, Precision is reproducibility, a degree of agreement among several measurements. We know that we can have random or indeterminate error, and there's an equal probability of a measurement being high or low. We also have systematic or determinate error, and this occurs in the same direction every time. So let's look at this graphic very quickly. We can see the darts are all over the place in the first um, diagram, which means it's neither accurate nor precise. In the second diagram, they are all grouped in the same location. So whatever the person was aiming for, they were really precise in their location because they all ended up relatively in the same place, but they were not accurate because the goal was to hit the target. In order to hit the target or get close to the target, uh, then we can be accurate and precise. So if you're both at the target and your darts are close together, you're accurate and precise. If we want to see something that is just accurate, that would be relatively close to the target, but they would be kind of spread out. If we're looking at our graduated cylinder here in exercise 1, we want to check the accuracy. If we want to check the accuracy of a graduated cylinder, the student filled the cylinder to the 25 ml mark using water delivered from a burette and then read the volume delivered. Following are the results of our 5 trials. So the volume on the graduated cylinder each time said 25 milliliters. But when we look at the volume shown by the burette, we see that the actual average was 26.54 milliliters. So the question is this cylinder accurate? The results of the trial shows very good precision because the graduated cylinder had the same amount each time, but that was far away from the actual average as shown by the burette. And so as a result, the graduated cylinder is not very accurate compared to the burette. As a result, there is systematic error that we have to be aware of in this case. So how do we battle these things? Well, the way we battle these things is through measurement and significant figures in our calculations. So sig figs is the abbreviation. You may have heard of these before. Numbers associated with measurement are obtained from some sort of measuring device. For example, the burette at the right measures liquid. The volume is read at the bottom of the liquid curve called the meniscus. That is something you will need to know because you need to know how to read glassware correctly. So the meniscus, here's the bottom, the bottom curve here, this bottom curve that they're referring to. So if you look at the bottom of that line there, I see that it's somewhere between my 2 marks here. So since the bottom of the curve is between 20.1 and 20.2 milliliters, we have to estimate the last digit. And a reasonable estimate would be 20.15 milliliters. Now, the first 3 digits in this measurement are considered certain digits because they come directly from the measuring device. You know exactly that the liquid is between 0.1 and 0.2, so 20.1, those are all certain digits. Certain, but this last digit was the one we had to make the guess for. I could have guessed 20.14, I could have guessed 20.17. As a result, Since these ones are certain, the last one is uncertain, then we have to be aware of the degree of uncertainty in all of our measurements. Because again, this can introduce some error. So it's important to establish a set of rules that indicate uncertainty in any measurement. These are the significant figure rules. So that means typically we always report certain digits plus one uncertain digit. Very important thing to know. All right, some rules. Determining sig fig numbers, determining the number of sig figs in a measurement. Non-zero digits are significant. A zero is significant if and only if it meets one of the conditions below. The zero in question is terminating and right of the decimal, must be both, or it's sandwiched between two significant figures. Excuse me. If it is an exact or a counting number, it's going to have an infinite number of significant figures. So for example, 98 apples is an exact number. That is an infinite number of significant figures. When we round, we're only going to round at the end of all calculations. We're going to use scientific notation for larger numbers. And examine the significant figure one place beyond your desired number of significant figures. If that digit, one place beyond, is 5 or greater, we round up. If it's less than 5, you drop the remaining digits. Don't double round. If the number 7.348 rounded to 2 sig figs is reported as 7.3, don't look at the 4 and say, oh, there's an 8 and round up, because then you would say, oh, it's 7.4. So 7.34 is what we're looking at here. 7.34. You look at this digit and you round down, so it's just 7.3. What I'm saying here is don't do this and think, oh, this would round up, so this is 7.35. Oh, and then that would round up, so this is 7.4. We don't want to do that, okay? Just be careful of that. So let's do some practice together. Here we go. Give the number of significant figures for each of the following experimental results. All right, so zeros in front of a number are not significant. So these first two zeros, they're called leading zeros, do not count. But my 1 is significant. This 0 is sandwiched between a 1 and a 5, so that's significant. And then the 5 is significant. There are 3 significant figures in this particular question. In the next one, we've got leading zeros again. So those are not significant, but I start with my first number. And then I have 2 zeros that are sandwiched between the 5 and the 8. Those are significant. The 8 is significant. And then the last 0 is terminating into the right of a number. So it had to be both. So there are 5 significant digits here. So 50080 are all significant. When we're looking at a number in scientific notation, you don't need to worry about the times 10 to the negative third part or times 10 to the whatever. You just need to look at the numbers given here. So I see a sandwich 0 and a terminating n to the right 0. So there are 4 significant figures in this problem. This next question asks us to rewrite 410,700,000 milligrams to show the correct sig figs. And you can use scientific notation. So for scientific notation, I've got, actually let me zoom in here because I think that will help us a little bit. All right, that's better, more space. So I need to look at my first 2 significant figures, which are 4 and 1. At the end of my number is an imaginary decimal point, and I need to count how many spaces to move that decimal point to the left. 1, 2, 3, 4, 5, 6, 7, 8. I always move it so it's right after the first number. So 4.1 times 10 to the 8th milligrams. That is 2 significant figures. If I wanted to do 3 significant figures, 4.10 would be my 3 sig figs. I have to look at the 7, which would round up. So 4.11 times 10 to the 8th milligrams. This is 2, this is 3 sig figs. If I wanted 4 sig figs, 4.107 times 10 to the 8th. Now the digit after the 7 is a 0, so I can just cut the number off there. And then my last one, 4.1070 times 10 to the 8th milligrams. And that would be 5 significant figures. All right, we're going to do one last set with some rounding here. Round the following numbers to 2 significant figures. So 1 and 4 are significant. I look at the 8, I have to round up. This is going to be 15 milliliters. These 2 zeros at the front are not significant, but the 9 is, the 0 is. I see the 9 at the end, which means I have to round up. 0.91 grams. Those are my 2 sig figs. I see a 1 and a 1 as significant. I see a 3, so we just cut off the 3 and the 6, 1.1 liters. Here, same deal, 4.0. The 3 would round down, so I cut off the 3 and the 4, times 10 to the 4th meters. But then in this one, 7.0, and I see the 8, that would round up, so 7.1 times 10 to the 2nd milliliters. All right, we've had quite a few examples. Why don't you go through and do you try it set 1? All right. At the end of this lesson, you'll be able to check all of your answers to you try it set 1. Let's talk about reporting the result of a calculation to the proper number of significant figures. When you are multiplying and dividing, the term with the least number of significant figures in your problem is the least accurate measurement. Therefore, our maximum number of significant figures are limited by our least accurate measurement. So in this first example, 4.56, I've got 3 sig figs times 1.4, which is 2 sig figs. So when I multiply, I can get the number 6.38, but since this number has 2 sig figs, I have to have 2 sig figs in my final answer, so it rounds up to 6.4. When we're talking about addition and subtraction, we use the least number of decimal places because the one with the least number of decimal places is the least accurate when it comes to addition and subtraction. So here I've got 2 decimal places in 12.11, I've got 1 decimal place in 18.0, and I've got 3 decimal places in 1.013. When I add these all together, I get 31.123, but I can only have 1 decimal place, so I have to chop off the 2 and the 3, and I end up with 31.1 as my final answer. With pHs, the number of significant figures in the least accurate measurement determines the number of decimal places on the reported pH. So usually that will be dependent on what kind of probe we use. Go ahead, pause the video and do you try it set 2 on sig fig calculations, remembering that with addition and subtraction, you look at decimal places. With multiplication and division, you look at the least number of sig figs.